Okay, so now we're going to be moving to the second part of Module 5, which is looking at just one section in Chapter 17. So I'm going to encourage you to take time to read Chapter 17, Section 17.2. There is a PowerPoint presentation out here, but what I want to do is kind of hit the highlights by going over the equations that you're going to find are going to be helpful for the problems that we're going to do. And then we're going to do a sample problem that is going to kind of bring everything together, okay? So I'm going to start by going underneath. So if you want to grab out a piece of paper and follow along, and these will be the equations that we're going to be using for this last short little section in Module 5. So I'm calling this Module 5, Chapter 17 equations. Now, as we look at this particular section or this module, we've been dealing with momentum, okay? In Chapter 13, we were looking at everything that was in a linear sense. So we were only worrying about, things, if you would, the last problems that we looked at, just looking horizontally and looking at mass times velocity, mass times velocity. And then if there was any external force acting, we would add in the impulse, okay? Now in Chapter 17, just like when we were in Module 3, Chapter 17 deals with, all right, what if something's rotating, okay? Something's rotating, now we have a little bit different variables to work with, but the systems still actually remain the same. So what we're looking at here is we want to look at system momenta, so plural for momentum, plus system, see, my lead just broke here. System, oh, yuck. System impulse is equal to system momentum. Now, just like it was before, I like to think of, on my left-hand side, this is going to be my before. Okay, this is my momentum going into before any type of impulse occurs. And I like to think of the impulse as the during. Okay, and then it's going to be equal to after, the momentum after. So any change in momentum that occurs has to be done through an impulse. Okay, so that impulse is here. We add it to the original momentum before, if you would, and then afterwards we combine those two, we get the after. So we can say that we're going to sum the angular momentum, which is H, and we're going to call that H1. We use capital H in this book. Plus, we're going to sum the impulse that occurs from condition 1 to 2 or before it to after. And then that's going to be equal to the angular momentum after. Now, if we expand each one of those out, we're going to have a plus or minus in front of moment of inertia times the angular velocity of our initial state. Okay, so angular velocity, W, if you would, 1. Plus or minus, and again, because these angular momentas and impulses are going to have direction associated with them, that's why the positive or negative is out front. And this is going to be moment times time, okay? Moment times time, capital M, so not lowercase, it's capital M. It's going to be equal to plus or minus I, moment of inertia, times the angular velocity after the impulse. So I kind of put this down here, moment of inertia, and this is going to be angular velocities. This one's going to be moment, and this is going to be time. Okay. And then again, moment of inertia, and then this is angular velocity. Okay, just so that you know what everything equals. Now, it's worth taking time to make sure that we understand the units that these are all going to be in. So as we get information, whether it's distances or times or masses, we know what the units are that they're in so that we come up with the appropriate units. So let's look at units. Okay, so let's first look at angular velocity. Okay, now in and out of these equations, it has to be in radians per second, whether I'm in the English system or the metric. We will be given in RPMs. In that case, you need to convert to or convert from RPMs. Okay, so the problem will give you starting, RPM is going to be this, and I want to get to, a final RPM. In and out of these equations, they have to be in radians per second. Okay, so you'll have to convert those to use those. Don't use those directly. I, as we know, is moment of inertia, and the units are going to be kilograms times meters squared for metric, and pounds times seconds squared times feet for English or standard units. Okay, so that means that any distances we have to have in the appropriate units, and any, forces or weights we have to have in the appropriate units or masses. Okay, capital M is moment. Okay, and we know moment is force times distance. Now, because we have rotational items here, that distance from the center of rotation is going to be a radius. Okay, so the units for this, we are familiar with newtons times meters or pounds times feet. Okay, so again, just being cognizant of we get information in that we, kind of get it in the right form. So that way, when we magically put our units at the end, we end up with the right number because we had everything in there appropriately. And then T is going to be equal time. And we know that for either one is going to be in seconds. Okay, bless you. Any questions right now about units? Okay. Now there's a couple other things that we got from other modules that they're worth putting down here, because in your homework and or on what we're going to be doing for our sample problem, it'll come in handy. So moment of inertia calculations. Okay. Here again. Moment of inertia. So general. Okay. Moment of inertia about its centroidal axis is going to be equal to mass times k squared. Okay. So we know that m is equal to mass. That needs to be in kilograms or in pound second squared divided by feet if we're in the English system, right? That's a slug. K is a radius of gyration. Okay, and that's going to be either in meters or in feet. Most often it's going to be given to you in a problem in millimeters or in inches. You have to convert it to meters or feet. Okay. K is radius of gyration. Now, if we have a disc or a cylinder, I is going to be equal to 1/2 mr squared, where r is the radius, okay? Not radius of gyration. It's just the radius from the center of rotation to the outermost material. This is when we have a disc that's solid or a cylinder that's solid, okay? And that radius is going to be in meters or feet distance, right? And then ones that we're going to be using in our application problems, you're going to need to know the moment of inertia of a cube. That's going to be 1/12 times the mass times one of the sides squared plus another side of that cube squared. Okay, so L is going to be the length of a side. And again, meters or feet. Okay. And then there's one last thing that we need to remember for, and it's going to be it's going to be in, I think it's a sample problem. We are going to need to remember velocity ratio of two gears. And we know that there's like 5 different things that we can use, but based on the information we're going to be using here, this is going to be, let's see, W1 divided by W2. So remember that 1 is equal to the driver and 2 is equal to driven, okay? Driver, when we're talking about angular velocity, is usually going to be the smaller gear and it's going to be rotating faster, okay? It's going to be equal to radius 2 over radius 1. They flip because we always want our larger number on the top. So the driven typically is going to be the larger size gear and going slower, okay? So those are going to be some things that we just need to recall. They might come in handy or they will come in handy for things that we're going to be doing. So even though we've hit these in different modules, rather than having to try to look for them, I thought we would put them on our equation sheet here for the second part of module 5, which is the chapter 17, section 2. So any questions right now on our equation sheet? Again, you have covered these individual items, whether it was in, well, in physics, you would have had it. So angular momentum or angular momentum as it goes around. And really, we're just transitioning from straight lines to rotating about a center, okay, and how to handle those. So our next task is going to be looking at a sample problem in this second section in chapter 15. And then using these concepts and these equations to solve a problem. So I'm going to kind of stop this here, and then we will start fresh on the sample problem.